Welcome to AP Precalculus. Today, we're diving into the relationship between exponential functions and a new type of function called a logarithmic function. Our main goal today is to construct and understand the inverse of an exponential function. This means by the end of this video, you will be able to represent the inverse of an exponential function in several ways. We'll cover the general form of this new function, explore its unique properties, learn how to switch between forms, and see what this relationship looks like graphically. In other words, you'll master how to work with logarithms. Before we jump into the inverse, let's briefly recap exponential growth. The key property of exponential growth is that as the input, x, changes by a constant amount, the output, y, changes by a constant multiplicative factor. That is, the outputs change multiplicatively when inputs change additively. For example, consider the simple exponential function, y equals 2 to the power of x. Here, our base, b, is 2. Let's look at its values. When x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 8. Notice that as x increases by 1 each time, y is multiplied by 2. This consistent multiplication is the hallmark of exponential growth. Now, the inverse function will reverse this process. So, it must take multiplicative changes in the input and produce additive changes in the output. This is the core idea of what we're about to explore. So, how do we find the inverse of an exponential function like y equals 2 to the x? The standard procedure for finding an inverse is to swap the roles of x and y, and then solve for y. Let's start with our function y equals 2 to the x. Step 1. Swap x and y to get x equals 2 to the y. Now, the challenge is to solve this for y. We need a way to get that exponent, y, by itself. This is where a new mathematical operation comes in, one we haven't seen before. It's called the logarithm. By definition, a logarithm is the operation that answers the question, to what power must I raise this base to get this result? So, in the equation x equals 2 to the y, the exponent y is what you get when you apply the logarithm with base 2 to x. This is read as y equals the log base 2 of x. It means y is the exponent you put on 2 to get x. This new function, y equals log base 2 of x, is the inverse of the original exponential function, y equals 2 to the x. Now let's formally define the logarithmic function and its general form. The general form of a logarithmic function is f of x equals a times the log base b of x, where b is greater than 0 but not equal to 1, and a is not equal to 0. Let's break that down. The b is called the base, just like the base of an exponential function. Since logarithms are inverses of exponentials, they share the same base. The number a is a vertical stretch or compression, which we'll explore later. A key takeaway is that every logarithmic function is the inverse of an exponential function with the same base. So, if you see f of x equals log base 5 of x, you know its inverse must be f inverse of x equals 5 to the x. Just like we saw that exponential functions have a unique pattern of growth, logarithmic functions have their own unique pattern. It's the reverse. While exponentials turn additive inputs into multiplicative outputs, logarithms turn multiplicative inputs into additive outputs. The outputs change additively when inputs change multiplicatively. Let's use our example, y equals log base 2 of x. To calculate this, we ask, 2 to what power equals x? So, if x is 1, y is 0 because 2 to the 0 is 1. If x is 2, y is 1. If x is 4, y is 2. And if x is 8, y is 3. Notice that as x doubles each time y increases by 1, so we are seeing the exact opposite of exponential growth. This pattern confirms their inverse relationship. The multiplicative input changes produce additive output changes. A very powerful way to confirm two functions are inverses is by composing them. That is, plugging one function into the other. When you compose inverse functions, they essentially undo each other and return the original input, x. Composition of inverse functions. F of f inverse of x equals x f inverse of x equals x. Let's use our functions. F of x equals 2 to the x, and its inverse, f inverse of x equals log base 2 of x. First, let's compose f with f inverse. This means we plug log base 2 of x into 2 to the power of x. We get 2 to the power of log base 2 of x. By the very definition of a logarithm, the base and the log base cancel out, leaving us with just x. Now let's compose in the other direction. We plug 2 to the x into log base 2 of x. This gives us log base 2 of 2 to the x, Again, the logarithm and the exponential with the same base cancel, leaving us with x. Since both compositions result in x, we have confirmed that these two functions are inverses. The inverse relationship between exponentials and logarithms is also beautifully represented graphically. It all comes down to symmetry. Graphically, any inverse function is a reflection of the original function across the line y equals x. Let's plot y equals 2 to the x. It has a y-intercept at 0, 1, passes through 1, 2, and 2, 4, and has a horizontal asymptote at y equals 0. Now let's add the line of reflection, y equals x. If we reflect the blue exponential graph across the red line, we get the black logarithmic graph, y equals log base 2 of x. Notice two key things about the logarithmic graph. First, the roles of the domain and range have swapped. The domain of the log function is 0, infinity, and its range is all real numbers. This is the exact opposite of the exponential function. Second, its intercept is now the x-intercept at 1, 0, and its asymptote is a vertical one at x equals 0. These are also inverses of the exponential's properties. This graphical reflection leads to another crucial property, the reversal of ordered pairs. The rule is simple. If a point with coordinates s, t, is on the graph of the exponential function, then the point with reversed coordinates, ts, is on the graph of its inverse logarithmic function. The x and y coordinates are literally swapped. Let's demonstrate this with our two functions. For f of x equals 2 to the x, let's look at the points we plotted. Now let's take each of those pairs and swap the order to get points for f inverse of x equals log base 2 of x. Let's check these. For the point 4, 2, on the log graph, it means log base 2 of 4 is 2. Is that true? Yes, because 2 squared is 4. This reversal of ordered pairs is a powerful tool. If you know a few points on an exponential graph, you can immediately write down the corresponding points on its inverse logarithmic graph. Let's summarize the key relationships between exponentials and their inverse, logarithms. These are the tools you'll use to work with these functions. First, the definition. An exponential equation, b to the power of y equals x, can always be rewritten as a logarithmic equation, y equals log base b of x. This is the fundamental bridge. Second, composition. As we saw, plugging an exponential into a logarithm of the same base, or vice versa, will always return your original input. They are inverses. Third, the graphical reflection. The graph of any logarithmic function is a reflection of its exponential counterpart across the line y equals x. And finally, the reversal of ordered pairs. The x and y coordinates on the graph of the exponential function are simply swapped to get the points on the graph of the logarithmic function. Let's work through a full example to solidify these concepts. We'll start with an exponential function, find its inverse, and verify it in multiple ways. Let's say our function is f of x equals 1/3 to the x. The base here is 1/3. First, find the inverse function. Step 1. Write f of x as y. Step 2. Swap x and y. So we get x equals 1/3 to the y. Step 3. Rewrite this in logarithmic form. Y equals log base 1/3 of x. This is our inverse function, f inverse of x. Next, let's verify using composition. If we plug f inverse of x into f, we get 1/3 to the power of log base 1/3 of x. The bases cancel, giving us x. If we plug f of x into f inverse, we get log base 1/3 of 1/3 to the x. The bases cancel, giving us x. Composition works. Finally, let's verify with points. For the exponential function, we have points like 0, 1, 1/1/3, and -1/3. For the logarithmic function, if we swap these points, we get 1, 0, 1/3, 1, and 3, -1. Let's check the first one. Is log base 1/3 of 1 equal to 0? Yes, because 1/3 to the power of 0 is 1. It all holds together. One final, but very important concept is how the growth rates of these inverse functions compare. We know exponential growth is incredibly fast. Logarithmic growth, its inverse, is much, much slower. The notes interpret logarithmic growth as slower than exponential growth. Think about it like this. For y equals 2 to the x, to get the output y to reach 65,536, you only need to go to an input of x equals 16. That's incredibly rapid growth. Now consider y equals log base 2 of x. To get the output y to reach a modest value like 10, you need an input x of 1,204. To get to 16, you need an input of 65,536. You need to put in very large numbers just to get the output to grow by a small additive amount. This difference in growth rate has massive implications. It's why things like pandemics, compound interest, and population growth are modeled with exponentials, while data compression and the scales for earthquakes and sound intensity are modeled with logarithms. So, let's quickly recap what we've learned. Logarithmic functions are the inverse of exponential functions. Y equals log base b of x means b to the power of y equals x. Their properties are opposites: domain, asymptotes, growth patterns. They are reflections across y equals x, and their ordered pairs swap, st becomes ts. We've learned that logarithms are simply a way to solve for an unknown exponent. This inverse relationship is fundamental. It reverses everything: the operation, the growth pattern, the graphs, and even the ordered pairs. Today, you've constructed representations of the inverse of an exponential function. You can now rewrite equations, check for inverses using composition, and interpret them graphically. Understanding this inverse relationship is the key to unlocking the powerful world of logarithmic functions, which you'll explore much more deeply in future math courses. Thank you for watching.